Okay to go? Yeah. Good morning, everyone. My name is Mike Gowell, and it's my pleasure today to introduce our next keynote speaker. I am really excited about this topic. I think that it's at the leading edge of the research that we need in the world today, so get ready for a good ride and some great discussion. I'd like to introduce you today to Professor Ling Liu. She's at the School of Computer Science at Georgia Institute of Technology. She has the Distributed Data Intensive Systems Lab there and many students working on projects in that lab. They look at performance, security, privacy, data management issues, all in the context of large-scale distributed computing systems. That lab is supported by NSF, DOE, DARPA, IBM, and HP. She's published over 300 international journal and conference proceedings. 300, that's pretty busy. Her research group has also produced open source software, WebCQ, XRAP Elite, PeerCrawl, and ShapeI, among others. She's been the Best Paper Award winner at numerous conferences, and she serves on many editorial boards, and one of the most important ones are Transactions on Services Computing. She's editor-in-chief. So I'm pleased to introduce Professor Liu to you now.
So thank you, Professor Gao, for introduction. I also would like to thank LJ and Jia and the conference steering committee to inviting me for give a keynote. It's my true pleasure to share some of my ideas and the research work with the audience. And I love to have a lot of tough questions. I hope to receive some more questions. So this topic is a topic that linked with services computing, because I'm going to talk a little bit at the very end if I have time. Basically, our conference has grown since 2003. Well, LJ was there with a couple people in the steering committee. And then 2004, and as we move on, more and more people joined. I joined the crew in 2004. So basically, there are lots of events going on, and we are continuously going to the new pages in the services computing. But it doesn't matter what comes into the hot space, that services computing is always something that is long-lasting. So that's one of the things it's worth for all of you to work in this area, dedicate your intelligence, your effort, and your research in this area. Okay, so the next challenge that I see is data analysis, analytics as a service. But it's a very, very difficult topic. So I'm going to pick up three interesting ideas. And three interesting ideas. Some of them I have done some work, and the others I have not started even. But I think it's a very interesting angle to looking at how do we deliver data analysis as a service. So where's the laser pointers? The first thing I want to mention a little bit is on the. Where's that? And I'm going to talk a little bit on the big data. Why big data pushes the service computing to have to looking at data analysis as a service. And then I'm going to talk about the three interesting opportunities and also three very hard challenges for making a data analysis as a service. But these are the things that if we do, probably we can actually lead the entire big data world to come to the service computing's a trajectory. And I will also talk a little bit of the common difficulties that we have to face as we move forward with that, but those are the difficulties that will not block the road. Okay, so that's the kind of things I'm going to talk a little bit. The first thing is big data. So what is big data? A lot of people talk about big data because they gave a different kind of definitions, including a Gartner's 3V, and a lot of companies promote that concept. But I like this concept the best, which is the big data is a concept. So it is not a stable, static concept. It's an evolving concept. Therefore, when we are defining big data challenge, always looking at those kind of data set that are beyond the ability of the current legacy applications that can understand, can analyze, can manage those data. Then we have a big data. And another thing is if you have a data using your current conventional a system that you have at your work or at your company, that you can no longer process those data because data grows out of the capacity of the existing conventional infrastructure. And then those are also big data challenges. And so therefore, big data becomes a dynamic, subjective, evolving concept rather than just a static, fixed, how much amount, how fast data generate, and how much variety. But actually, they are continuously changing as our ability to handling data grows, then big data becomes changing the definition. But this fundamental a bond has always been there. As long as we have a human being that on the earth that are different to each other, has limitations, then these limitations don't last because these are created by humans. Okay. So next thing I want to mention a little bit is analytics. If we look at the data analytics, actually they have been many years of history. From the moment that the algorithm start, before the computing even is born, that we have all these analytics. So if you look at the descriptive analytics, that we have developed so many tools. We have so many tools, so many systems that are doing descriptive analytics. For example, database system is one of the very successful systems, and they are consolidated all kind of data query, data report into a single infrastructure that provide a database services for all the clients, all the companies, for all kind of data. So that's basically is one kind of analytics. As we go, we have a lot of file systems, and they are all very successful in providing descriptive analytics. They are the tools, services for descriptive analytics. As we move the intelligence up, then we are looking at more predictive analytics, where we are interested in looking at what are the statistic models. Yeah, what are the statistic models for looking at what his data is telling, and what are the predictions we can do? What are the errors that along with those predictions? What are the confidence along with those predictions? And what are the optimization for those kind of non-linear learning models? So these are actually the area that big data, machine learning, data mining are really hot on. So now we are going to look at problems in this area. So now let's look at the 3 opportunities. So that's what I'm going to focus on. I'm going to give you the examples, what I mean by that. So the first opportunity is, if you look at all the algorithm research, data mining research, machine learning research, there are many of them using the common algorithm model, common computational optimization, but they are solving very different problems with very different domain focus. And so therefore, it's time for us to look at what are the common programmable abstractions. And those common programmable algorithm abstractions can be easily turned into a computational building blocks that can provide much efficient implementation and optimization, allows many algorithms to benefit. And that would also make the data analytics a lot faster, a lot easier to manage, to control, and allows domain scientists, the data mining algorithm theoreticians to focus on those that are beyond the commonality that has been well understood. Okay, so that's one of the areas I want to mention a little bit. I'll give you examples. And the second area that I think is also very, very important is the how do we reconsider a lot of data structure, data access algorithms, which are designed to reduce random access by adding sequential access capability. For example, indexing is a very, very well-known example. Data layout on the disk in the memory, they are not very laid out in the way you want to sequentially access them. Therefore, build a different index. Each index represents one sequential way of accessing your data. Therefore, you can access data a little faster. Okay? But nowadays, we're looking at how do we parallel processing data. Therefore, we need to look at what are the unconventional access models that we could invent and to speed up data processing. Because traditional models, they are not really optimized in memory usage. They're not optimizing in network I/O, disk I/O at all. Okay, so we'll talk a little bit on that as well. And that is another innovation that helps the analytics to become really a service. Because you don't want to produce a service, you want to produce a high-performance services. Okay, the last one is another interesting thing that I really like, which is if you look at the human intelligence, nobody is smart. Okay, if you get into the PhD level, then your advisor probably tell you, okay, every PhD student I have, they have their own strengths and weaknesses. They're all smart in their own ways because we all have certain strengths. So now, for the algorithm design, traditionally, we are all looking for best algorithm. My algorithm is the best, the world the best. I beat everybody else. But we are now coming to a stage that this kind of algorithm probably you'll never find. You only beat some other people that you selected to beat. And those are maybe known algorithms, but maybe there are other algorithms out there you cannot beat. Therefore, nobody is the best. You cannot say Hadoop MapReduce is best. You cannot say Spark is best. They are not best. You can easily beat them. You can easily find a case, you will beat them. Okay? So the question means, this is basically means nobody is best. So therefore, how do we actually encourage innovations? By finding the smartest way to leveraging multiple algorithms, multiple learning models, multiple optimizations, and to produce the best result. Okay, so we'll talk about examples of successful stories in that area. And that's basically the 3 opportunities I want to talk about. And all 3 opportunities are actually a focus on 2 fundamental questions. So the first question is, if I have lots of data, so what part of data, what piece of data that I should use to do analysis? Maybe not everything I want to use. Okay, and if I want to perform analysis, how do I do it more efficiently, faster? So these are the 2 questions. Doesn't matter what analytics you want to do, and doesn't matter what algorithm you want to develop, you're going to answer these questions. And algorithm differences depends on what kind of data they use to learn, and how do they digest those data to learn, and then how do they efficiently implement the algorithms. Okay, so let's look at the first opportunity. So the first opportunity involves a lot of areas. I'm going to use a discrete optimization problems. Why? Because that's everybody can understand. So first thing I want to talk about is I'll talk about 2 case studies. One is a social network analysis. Everybody understand, which is you have a social network with, let's say, 40,000 nodes, and they represent a people. And then your company, you have a budget to do advertisement. But you want to select only K people in this giant social network because you only have this much budget to do advertisement. So now, which K people you're going to select to give them the free product? And so they can actually propagate their experiences over the social network. And the goal is to reach every corner of the social network and make the maximum influence out of the social network through this K budgeted product. Now this is a very, very interesting problem. A lot of companies study, a lot of researchers study. The number of papers generated in this area, if you Google it, probably on the order of thousands. Okay, but they all use the same algorithm. They all use the same algorithm at the end. But they differ in a little bit in the kind of utility they want to maximize. Okay, now if you look at the sensor domain, in the sensor networks, we have even more papers, maybe on the order of 10,000 papers. Okay, most of sensor networks, one of the fundamental problems in sensor networks is you have a limited budget to buy sensors. Therefore, you cannot possibly place sensor on every corner of the Earth. So what you do is you place sensor at a certain selected point, locations in the Earth, and then you study it. For example, we have a water network. Every city has a fresh water network. And one of the important investment for water company is to make sure the water pollution level is very low and to periodically put in chlorines to make sure the water is not infected. And at the same time, the chlorine amount cannot be too much, otherwise the human would feel uncomfortable. So these are the typical cases. Now, the water sensor, quality sensor, is very expensive, typically on the order of 5 digits. So you cannot place a lot. So now the problem again is, okay, in the entire water network, where I should place sensor? How do I place them, and how do I dynamically change the placement of that to make sure my detection of the water contamination is efficient and it's timely? Okay, now this is the same problem as social influence analysis in social network, identical. But there's a difference. The utility function for what is kind of influence computation is different. But the fundamentals are the same. So let's look at the K most influential people. How do we compute? If you follow me, you can understand it. You don't have to understand math, you can understand this. Okay? If you have a set of people that are network node, and if you want to select a subset of this node, that you want to give out the samples to see whether they can be the most influential subset. How do you do that? Then what you do is, if you want to find a subset, that means you want to find a subset A. Doesn't matter how many people in it, depends on your budget. Let's say my budget is K people. Then my budget would be constrained as K. And then I need to define a function. The function would be maximum propagation of the good positive experiences. Okay, so you compute that. That is domain specific. Somebody has developed this function. But once I have this function, the entire computation is the same, identical. If you look at all the papers, the function f is defined differently. And the computation, they're all using the same algorithm. Same matrix manipulation, same computation model, okay? And then what you do is, this is an NP-hard problem. Can't do it because it's big combinatorial enumeration, okay? So therefore, let's do a greedy approximation. So everybody is doing greedy approximation for NP-hard problem. So how do you do greedy approximation? Very simple. So you start with assuming this A set is empty. And then you start by only locating every node in the network. For each node, you compute his influence. How to compute? Simple. You have to define this function. If the function I define is just look at all your neighbors, count on how many neighbors you have, and using them as your influence, that's one model. Second model say, okay, count your neighbors, count your neighbors' neighbors, count your neighbors' neighbors, count 3 houses away from you, and count using that as your influence. So you can define any function you want, and that's a function. And papers are different in that function. However, the computation is the same. Once I have the function, all I need to do is for each item, I compute his influence value. Then among all the 40,000 people, I find the one best guy who has the most influence. And then for every 2 people, I do the computation again. Every 3 people, I do the computation again. Every K people, I do the computation again. And among all these computations, I pick the number 1. And that subset would be my subset that I want. Now, this is a greedy approach because they are not theoretically guaranteed optimal. However, if you have the function that is following certain features, then the theoretician already approved the greedy approximate very closely to optimal. So therefore, greedy simplification works really beautifully, but you have to have a certain property, which is if your function actually is a monotonic function, is a submodular function, then the big theoretician has shown, okay, theoretically, formally proved that the approximation is about 63%. So it's very high approximation. Therefore, you can use greedy algorithm really compute this. And you can solve the NP-hard problem using a much simpler solutions, and you can even optimize greedy algorithms. Okay, so that's actually the beauty of this thing. Okay. So now, what is monotonicity? So monotonicity in the set concept is basically if you have a 2-item set, you have a 4-item set. Then if you add same person or same sensor into the network, and you add to the smaller one and smaller one, sorry, I don't have any image on this. Okay, if you have the two set, one is a small set, that's A, only have 2 items. One is a bigger set, B, has 4 items. Then if you compute their influence, let's say their propagation coverage, whatever the function you have, typically if your function is designed in such a way, for smaller set, the utility is always smaller than the bigger set. Even though their difference not big, but they are smaller. So the bigger set always has higher utility. Smaller set always has a little bit smaller utility or equal utility. Then you are following monotonicity. Now, that's the first thing. Second thing, we want the function following next property called the diminishing return. Now, these are the model probably in economics used a lot. Probably Professor Michael Gao knows a lot on this, right? So the diminishing return means that if you have a small set, you have a bigger set. If you want to add one more investment into these 2 sets, then the smaller set has a higher return, the bigger set has a smaller return. So that follows diminishing return property. So the diminishing return property is also very common. So this submodular function is very common, and most of the social economical functions are all following submodular property. Now the interesting thing is the theoreticians trying to prove every function they design are submodular. The formal proof that. So that is theoretical research. Already for every utility function you design, they start trying to formally prove this is submodular. Because if it's a submodular, you can use a greedy operation, you can use the greedy algorithm and the greedy optimization to implement that. So therefore, those papers already have logged. Now, besides those papers, the algorithm people generate a lot of algorithms. They assume I can use a theoretical result to show this function submodular. Therefore, now all I need is to find the greedy optimization. So then we have lots of papers too. So therefore, every paper, every algorithm have their own implementation. The world is flooded with algorithms. And then the implementation, a developer, software developer, doesn't know where to start. They start implementing every little algorithm. Okay, so we need a consolidation. So just like a database is some sort of consolidation of descriptive learning models, some basic descriptive learning models. It's a time for us to also thinking, what are the consolidation we can do? But in the analytic domain, there's no way you can find one single model that cover all. But you can find some domains like a discrete optimization is this set of problem. Maybe there is a way to find one. And for example, MapReduce is one of the computation model that abstract embarrassingly parallel computation, simple computation. That's why MapReduce is a beautiful model. They gave an example such abstraction is really valid, is going to work. But MapReduce is not invented to cover everything. So we need to continue to innovate in this space. So now I'm giving you another cool example, give you an idea to consolidate what I said. So if you have a massage chair, you know, people on the age of 50, they love massage chairs, okay? So massage chair, how do they make the cost reduce? Typically, you need a massage sensor sheet that covered is dense uniform sensing. And therefore, the massage chair with that sensing capability is very expensive. If you equip each sensor per square centimeter, then you are looking at, you can sense all kind of way of sitting, different way of sitting. Then your price is going to be very expensive. So to reduce that, researchers are looking at, maybe we don't need everywhere, just like a water network, just like a social influence, we have limited budget. Let's use the budget to design where to place sensor to cut down the cost. So then that's actually people doing study on that. Okay, one of the things people looking at is basically saying that let's place sensor in a selected spot based on what is the commonality among humans who sit in that kind of posture. So maybe we put the sensor in those places, and then we can cut down the cost to significantly lower for sensor part. not the rest of the chair. Okay, it's just sensor part. If I cut $100 sensor part, then I can make the chair more comfortable with leather cover, with all kind of mechanics, movement, with computer monitoring, remote control. Then you can add more cost, but overall the cost will be reduced. So that's actually one of the studies shows actually you can actually using very cheap algorithm to make it so cheap that a sensor no longer becomes very high end cost for that. And still people are relatively happy with the chairs. Now, of course, if they want to, they have a lot more money, they can spend it, they can make much higher precision sensor that are customized for particular customers. So now, interesting thing is, I also dig out number. So if I only select this number of sensors, if I just randomly place in a chair, I don't even have algorithm, then I get about 53%. Not too bad, actually. If I would uniformly place them, I get 73%. So you just optimize, you get a slightly like 8% more. Okay, so therefore, a lot of algorithms says that it's a concept, it's idea, it's modeling that helps you optimize significantly. And then the algorithmic tuning can give you another layer of optimization that are harder to achieve, which is very true. Okay, so now if you look at so many different applications, they are all discrete optimization problems. And they are all having a set of network and a set of graph. You want to look at a subgraph that has some features. Not all subset of node has certain features. Like there are lots of them. Okay, so for this set of problems, if we could develop a programmable abstraction model that allows the algorithm designers and domain scientists to just write a utility function. And then the entire infrastructure is there for them to run it on a distributed cluster platform, handling any size of data they want. That would be beautiful. And then that will be some sort of a services. And whoever made that invention, I'm sure you're going to be rich. Okay, I'm sure you're going to be rich. Okay? So that's actually one of the things that are interesting, and this is related with we're utilizing greedy approximation, theoretical outcome, and to look at a set of discrete optimization problems, we're looking at how we can benefit with that. Okay, now let's look at the next opportunity. I'll be a little faster because I'm trying to not be too late. And the next problem is computational abstraction. Okay, so doesn't matter what kind of data we process, what kind of algorithm we already have developed for that type of data. And because today the memory technology, the cluster computer technology, the virtualization, and the distributed computing, they all advance a lot. Therefore, there are lots more technology that are out there as hardware infrastructure. How do we utilize that in the best way? We should actually rethink how to increase the parallel computation capability. And by rethinking that requires a lot of understanding about the problem domain, about the data type, about the computational platforms. So this one, I'm going to just use one example because I only have understanding in this domain. There are other data sets we need to study. So I'm going to look at the graph domain because I worked a lot recently in the last 4 years on graphs. Okay, but it doesn't matter graph or whatever the data, the common technical challenge is the same, which is, doesn't matter how many memory you have. You may have a memory 50 GB, 100 GB, 1,000 GB. They are still too little, not enough to process a lot of data. Okay, so therefore we always deal with the limited memory, limited CPU, and how we are going to design the algorithm to fully utilize that. If you look at a Spark platform and MapReduce platform for Hadoops, the only significant difference between these two platforms, in addition to the fundamental thinking in terms of programming, is Spark try to utilize all the memory is out there. Okay, and a Hadoop MapReduce, because the way they implement the whole system is using Java virtual machine and dynamically sprung Java virtual machine. Every Java virtual machine they sprung, they need a certain allocation. So therefore, they cannot fully utilize the entire capacity. Okay, so that's actually one of the problems, of course. So the goal here is how do we actually design computational model that can maximize or can better utilize resources. So I'm going to use a graph as an example. If you look at a graph, there's so many algorithms. There are many textbooks on graph theory. And then even the graph learning kernel, there are so many of them. Traversal-based, shortest path-based, flow-based, all kinds of them. So, and then if you look at the metrics that people use to evaluate those algorithms, they also have a lot. They take a sparsity, density, and static, dynamic, all kind of factors they take into consideration. So there is very difficult area to get started because too many papers. So now, but if you look at it carefully, there's only two camps of graph computation. One is graph query, which is simply just give you a subgraph as a query, a search key. Find all the metrics in this whole graph about this subgraph. That's called graph query. Because the query now is not like a database query anymore. Because when you query something in the graph, you query a subgraph. If you want to query one vertex, that's an extreme graph. But if you want to query a set of nodes linked in certain ways, then you can find that. Okay? And the second set is iterative algorithms, which is like a page rank and shortest path, a single source shortest path, connected graph, and all the other type like a matrix multiplication and graph clustering, graph classification. They are all iterative algorithms. Now let's look at what they do. What do they do? Typically in the graph domain, the reason is very difficult is because the graph is growing too fast. And the things that can be modeled as networks are too many. Therefore, requires a lot of storage and it requires a lot of capability to take the data out of storage and in order to compute. However, graph is not like a relational table. You can just process row by row because graphs are connected. One vertex connects to another, another connects to another, another connects to another. The whole graph is connected. So where you cut? Where you do? You do not know. So therefore, this high correlation makes the processing so hard because either you fit the entire graph into the memory or it cannot work. But all the existing algorithms are assuming graph can fit into memory. Therefore, they don't have any other way to processing graph. Only one way. Whole graph in the memory, then I'll process it. Okay, so, and then the advance in the MATLAB domain is to say, okay, if you model graph into a matrix, I can cut matrix into blocks. Therefore, MATLAB today is still the fastest programming language that can make a graph processing faster. Okay, you can write the Java code, you cannot beat MATLAB. Okay, so now, of course, you can write the MATLAB code but translate into Java. That's you can do. Okay, next thing is the graph has such a skewness everywhere. So you have a vertex that the degree of the vertex are very different. So therefore, if you use a vertex-centric programming, you treat each vertex as an object. Now you can never load balance because object has very skewness. Some vertex has high degree with billions of funds. Some vertex has only 2. So how do you make a multi-thread processing on that? The thread working on a tool is finished in one fraction of a second. The thread with billions of neighbors is going to crunching. So then all the other sides dangling waiting because the CPU is not utilized. Memory is used, but CPU is not. Okay, so that's actually the difficulty. So that's why this area is a big open area. Okay, now I want to mention a little bit of the scale of a graph query. It's a hard problem actually. And if this is my query, I want to find what are the node that has this kind of a graph structure. So they have a reference like this, and I want to find all those nodes. So now in this graph, if you use the human eyes, how quick can you find it? It's not easy. Now you use a computer program, it's very fast, you'll find it. So if the whole graph is fit in the memory, there are zillions of algorithms you can find. Open source, they can find it for you. But next question is, what if your graph does not fit in the memory? Sorry, it crashed out of memory. Okay, so now Do they have something that you can program that you can do it in a distributed way or in a staged fashion? Do not know. Why? Because it's hard. Because if I cut a graph this way, I will never find it. I have to load this part and this part to find these two. What if there's another one? So what if there's another one? So wherever you cut, if that cut part reflects your answers, you're going to lose that. Okay, so that's what we have state of art. So now, how do you partition graph to do this kind of thing? It's a hard problem. Okay, we did a little bit of work. We had a publication, but we had an open source tool, but it's just the beginning. There are lots of problems still. Okay, we just did a little bit better than what we have today. Okay. Next thing is when the graph grows. So this is a 500 million vertices, and this is 8,000 million vertices. So when you have 8,000 million vertices, the graph takes much longer. It's 8 million vertices. 8 million edges. Vertices normally smaller than edges. So 8 million edges take half hour to run this graph query. So now if you look at what we have the graph today, the graph is big. No graph is 8 million edges. They're a lot bigger than that. You see the web scale, most of the social networks on this order. Now the web pages on this order. If you look at the brain scales, no one can actually even touch it. Okay, so for people to study brain analysis, brain diseases, that'll be a lot harder. And you can only do sampling. You can't do the whole graphs because you cannot process it. Okay, because we don't have that fast algorithms. Okay, now I give you an example. Here is a 3-graph system. MongoDB is one of the most popular commercial systems. And RDF3X is one of the systems from Germany, and it's an academic system, open source. And TripleBit is one of the systems we have developed. So the question here is, if you look at the graph itself, it's only this much, not big. 1 billion edges and 500 million edges. But look at the virtual memory they need. Okay, look at the virtual memory they need. For the same graph, different systems need a different virtual memory and physical memory to work. Okay, and because not only you load the entire graph into it, if you do computation, all the computation intermediate results you need it. All the auxiliary structure you need to do computation, you need it load into memory. So the memory is blown up very fast. And then now today's memory, we have a virtual memory, we have a real physical memory. So if you need a lot of virtual memory, guess what? You wait. Why? The virtual memory doesn't have space to fit more. Okay, you wait. I'll swap virtual memory out. Okay, the physical memory out of virtual memory, and then you can do. So this tiny little virtual memory becomes a busy swapping. They don't do anything work. They don't do real work at all. So that's actually why MongoDB is a little worse. But the interesting thing is, these two systems, nobody actually even do memory optimization. All they did is data structure. They try to reduce the amount of a random access by making it more sequentialized. And they try to use compression. They try to use a different type of indexing to optimize it. It's all on a higher level. But still, this is a very interesting result. Okay, so it means this area is still open. So basically, the solution for new algorithm is basically we need entire new thinking. And looking at the graph, looking at the correlation, let's think about what is the way we could partition this data and preserving the computation requirement. So that's actually is one of the interesting things. And so we have done a little bit of work by taking an innovative view, by looking at the graph not as 2D matrix, which is both dimensions are the set of vertices. And the cells in the matrix is the relationship between the two vertices. If you have edge, you have 1. If you don't have edge, you have 0. So we say, let's don't take that view. Because that view have one shortcoming, which is the vertex has a very high degree, have many, many ones. But the vertex is a very low degree, the whole matrix is empty. It's just unfilled. So therefore, if you process that kind of matrix, you waste a lot of CPU and I/O cost just for loading the junk into the memory. Okay, so what we're thinking about is maybe we look at the graph as a 3D dimension. And maybe you have a source vertex, you have destination vertex, you have edges, weight. And then we cut it in more dimensions. Now, it doesn't matter whether this is good or not. This is better than what we have now, but it may not be the best, okay? But this way of doing it, we actually can cut a graph like this into these 4 pieces. Now you can see these 4 pieces. They are very similar in terms of number of vertices, in terms of number of edges. Our goal is we cut the graph in such a way, not only they can compute together, but each piece have a similar amount of work. Therefore, we can load balance. We can multi-thread it. Okay, so with multi-threading, it's way faster in processing. So that's actually the general idea. Of course, the system we have still have issues, right? But the idea is plausible, okay? And another idea we had is trying to increase the locality in the data placement that reflect data access capability. So if you access vertex, always access vertex by in degree, because when you do page rank computation, all you need to compute my rank is using all the pages pointing to me. Therefore, you want to store me with those pages in one chunk, because then computing me is faster. Okay, so these are general ideas. So basically, by using that, we actually did some systems. You can see our system. We don't have a big machine, so we have a 12 GB machine, and we have 21 of them, and the total combined cluster a memory is only 252 GB. Okay, and then we run, and then if you look at the Sparks, the Sparks typically their machine is a 68 GB or above. Okay, this one is a 68 GB with a 16 node. Total compound memory is 1,088 GB. Okay, and then if you look at the Graph Lab, Graph 1.1 on Hadoop, Graph Plus on Hadoop, you can see the same. Graph Plus on Hadoop actually is a recent enhancement of Hadoop, a consortium. So they improved the Graph 1.1, taking advantage of Spark and the Graph Lab and other academic development, try to enhance the graph support system. So they show they have a more enhancement. But the interesting thing here is you can see there is an opportunity to improve. Doesn't mean Spark and Hadoop MapReduce Hadoop graph system, they're not good. They're good, but they're not efficient still. They are the first product out there allows people to use it. So there are still many problems with that. So by discovering those problems, by tackling each problem one at a time, probably we can advance a lot better. Okay? So that's actually what I'm trying to show here. And again, there are still failures. Okay? With such a big memory, and you still have failures. So imagine we're not even looking at a graph that are big. Okay, these are not big graph at all. Okay, they're not the graph big graph. They are not even in the full social scale, full web scale at all. Okay, they're small. Okay, and if you look at most of the reported data, their graphs are small. Even the open source graph, you can find big ones. Okay, the graph500.org has a huge graphs there. Okay, so now the question here is scaling analytics over big data requires also some interesting abstraction that you take a constraints you have, like minimizing the internode communication, maximizing the intranode communication, and then you can think in different ways of partition your computation and partition your data based on resource awareness, based on your application objectives. So these are all beautiful opportunities. And if you can take one problem, tackle it, hoping that it can solve multiple set of problems, then you are working on making analytics as a service. Okay. Last thing I want to mention, and it's also a fun thing, which is our algorithms. Okay. So we have too many algorithms. Some of them do the same thing we talk about. Some of them actually do not the same thing. They complement each other. They are not identical. Okay, they have a same. They are solving the same problem with a different angle, different dimensions. So one of the most successful example is IBM's Jeopardy, the Dr. Watson. Okay, And Dr. Watson does not have a lot of secrecy inside, but there are enough document videos out there we can dig out things. So one of the things that Dr. Watson used is a fundamentally new thinking. The first thing they did is assumption. So the hypothesis of research is fundamentally changed. Dr. Watson's group thinks no single algorithm is going to work. Okay, you want to beat human, you cannot use a single algorithm to beat human. You're going to use a collection of smart algorithms to beat human. Okay, so therefore, they take a fundamentally different approach because their research hypothesis is different. So then their approach is, okay, I'm going to do a multi-channel learning. I'm going to look at all the algorithms, giving one question. I'm going to fire more than 100 algorithms going around and independently study the same data set and try to dig out answers. And I'm going to take the top set of return, and I do majority voting. If a majority says the same answer, this is my answer, Dr. Watson's answer. Okay, and this has proved to be quite successful for you and smarter than you think, because those are static library of data. But these are not proved to be very successful for medical domain, for doctors, because doctor doesn't have a stable set of data they make diagnosis. They use the data and their brain and their experience to make a diagnosis. The experience is not easy to capture. Okay, so that's why this is a successful in certain type of domain, but how to make this even more successful in a more challenging domain is still a problem. The next thing I want to mention is time series correlation. You know, in the emergency room, ICUs in US, every ICU is fully packed with patients. Those patients are the patients have multiple indicators they are not doing really well. They're really in dangerous situation. However, doctor said sometimes those indicators are caused by drugs because we have to use a drug to treat them. Therefore, the drug has a side effect. Therefore, in each ICU unit, if you go, I visited Emory University, they have a 12 sensor or more than 12 body sensors. You have a computer screen display all of them. And then you will hear every room beeping. Beep, 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 beep. Why? Because every time the sensor is above the threshold of the medical domain decide its dangerous threshold, they beep. Now all these doctors still laughing, chatting, they don't do anything. Then I asked them, what's going on? Aren't you be nervous every day? This is beeping all the time. It's getting really nervous. They said, no, because if they're not beeping, they're not sitting here. If they're coming to this room, they're beeping all the time. So then I said, then how do you solve this problem? He said, oh, that's why we need you guys, right? Because we do not know how to solve this problem. Because some people, the sensors beeping, some people not. And if you look at those not beeping indicator, they are getting recovered. If you look at the beepings, you do not know whether they get recovered or not. So it's difficult to say. So do you have some thing to do? And actually, they said, we start a stock market. We think we are similar to stock market, but we are much more complex. But we studied stock market for quite a while. We even assigned our students to study. We still have no solution. And then I have no answer. I don't have a solution also. So let's look at stock market. Because after that, I actually went to look at the stock market research. 30-year stock market research started with only one sensor, which is stock price sensor. They collect stock price value every year after year, month after year, day after day. They use that to do historical correlation analysis, statistical analysis. And then they add news as a sensor, they add volume as a sensor. The entire stock market analysis using 3 sensors. And even with these 3 sensors, the stock market volatility prediction never good. Nobody make money out of that prediction. They need a lot of programmers. They pay high-price programmers to actually do certain kind of individual hikings to the value. Why? This is the reason. If easy case, all the 3 sensors giving you a beautiful, consistent view, they're all done indicator. Then you say, oh, tomorrow probably the stock price is going down. So that's easy. But most of the time you don't have easy cases. You have hard cases. So some of the, giving a window, some of them going down, some of them going up. Now the next problem is, how do you do the window? If you make window small, make window big, their indicator different. So that's why it's a very difficult problem. And the stock market study 30 years with this much money. And then they have put so many mathematicians. And they work on this. They have not had a good solution. Now, medical domain, you're looking at a sensor on the order of 20, 30. What are you going to do? Okay, so that's why medical domain doctors said we are frustrated. We do not know what to do. And I said, then how you make a decision based on our experience? Those medical school graduates, they do not know anything because they will be scared. So we learned through experience. I have seen this patient pass away. So if there's somebody similar, I think he's dangerous, right? Because I have seen this guy, similar cases that are gone. I've also seen another cases similar. He's recovered. He's going home fine. So that's what they do. Okay, and if you see your doctor a lot, you know your doctor also doing a lot of experience-based diagnosis. Okay, so now the observation here is open domain. We have a lot of opportunity for young people to work on it. Pick up a domain, do an in-depth study, and then you probably can find something interesting to do. And also almost every data type, every algorithm, somebody already touched it. But they may not be good enough, okay? So that's actually what I want to say. Basically, there are a lot of opportunity for us. And if you do research by thinking, I want to make a data analysis as a service, then you will look at the commonality. You will look at those components that can help the data analysis to become a service. And then you will look at those abstractions. Actually, you will advance the field better. So that's why service-based thinking help you to do better research. And in the past 40 years, we have been looking at the independent algorithms and look at convexity-based optimizations. In the next 40 years, if we are looking at making things as a service, maybe we'll change the way how we think the computation should be, the system should be built. Maybe we'll do better. Okay? And a number of things that are open. Privacy is a concern. Quality is a concern. Okay? Privacy is one of the dark side of analysis, and quality is another dark side of analysis. But big data is here to stay. Nobody can take it away. Therefore, we have to deal with privacy, deal with quality. So I attended a workshop on this. So first, let's look at privacy for those people who do not know what is privacy. So this is a very interesting case. So Adam, everybody know. If you watch the Mythbusters, then you know, because my daughter loves it. We follow her, always watch this. So, and he basically one day when he leave the house, he just posted, I'm going home, going to office. And then a lot of people started using that, dig out where is his home and what his car he drives when he leaves job, and they post it on the internet. Okay, so that means anything you tell, people can actually infer things. But today, even you tell your friends gossips around, and if you share certain kind of messages on the public domain, then the things can actually go out of hand. Now, the question I really loved is these 3 questions. So I had a workshop. They asked these 3 questions. I was in the panel. They said, the panel moderator is a great moderator. So he said, okay, I want you to answer these 3 questions. Everybody has to say something. The first question is, what is the biggest threat to privacy? Is it government? Is it social media? Is it advertiser, data brokers, or ourselves? Okay, second question, is privacy really dead? And because younger generation loves social network, loves Instagram, loves messaging, so you cannot prevent that. You cannot tell your daughter, your son, don't do that. They will not listen. And the sense of privacy is even less with the young generation. And then last question, what is the most promising technological solution for protecting privacy? What are the most hyped? Okay, very hard question. Okay, the first set of questions is basically, I believe, okay, nobody is the biggest threat for the privacy. It's ourselves. We need to have a better understanding of data privacy based on data utility. Because we love internet, we love instant messaging, we love social media. Therefore, we have to learn what are the things we want to protect. What are the utility we want to protect? We need to develop a utility-based privacy protection policies and privacy protection compliances. and we need to set them into laws, into the softwares. And this is way far from even beginning. And the second thing is privacy dead? No. But the definition of defining privacy based on the amount of information you share is dead. It will never be there anymore. So privacy should not be defined by the amount of information you share, but rather by amount of information that it can be protected based on your wish. Okay, now how do we define that? I do not know. Okay, last question, I do not know what's the answer. Okay, and quality. And everybody knows Google flow trend is a big a headline. And then right after that Google the announcement, the Nature published an article, announced that Google's big flow trend analysis really not good compared to CDC. Because the CDC uses a very traditional method, and based on doctor's report, and the CDC data is much more accurate compared to the reality. And the Google is doubles the inaccuracy. Okay, and if you look at the Google's lines compared with the CDC lines, you can see the gap. The Google is red, and the CDC is lowest curves. So you can find the article. I put it there. This slide is posted on the conference. You can find it. Okay. So basically, it's fun. It's a big, interesting discussion. And this discussion is much more pronounced than any other doctor or other things, people's discussion. So now what we take away from these lessons is basically big data analysis is powerful, but you should not think it as something that is magic. And you should treat it as just complementary. It's just additional reference book. It's not the reference book. It's just one reference book. So you still have to study what things are missing in this big data, what things are missing in this analysis. You also need to understand, even though big data is here, you did a big data analysis, you did not have a big insight yet, because a big insight requires quality analysis. And if you do not know the data quality, you do not know the analysis quality, you cannot even say anything. And the big data's problem exists in small data, because the doctor using small data to do statistical analysis, and they don't even want to share data across labs because they don't trust other doctors' data, because they don't trust the way doctors collect data. So therefore, big data can make a grand scale mistakes that are really, really dangerous, can hurt us back very badly. So we should be careful. Last thing is that we should really, really think of big data as a complementary signal, not as a decision-making reference, okay? So that's why the doctor said, you computer science always want to do analysis, replace me. And don't dream about it, okay? My experience is not a medical school experience that you can learn from computers, because my experience can never be learned by computer, okay? That is true, okay? So that's why I think it's interesting. Now I want to do an acknowledgement. I entered this service field because LJ invited me to be the PC chair on 2004, a conference. Then I learned what is service computing, what is service-oriented architecture, this whole thing. And then I started involved in this conference for, I have an animation, they don't go? Okay, play, okay, they're slow. So basically, it's not playing. Why is not playing? Where I should push, they're not playing. Projector doesn't do, oh, okay, now it's playing. Okay, so, and then I have lots of people involved in this conference I get to know that I would never know through my traditional research communities. It was a pleasure and a tag along and get me to see new view of the research problem we deal with. So I thought it was fun. And another thing that I want to say is that the entire conference grows significantly, remarkably, that beyond my imagination. Okay, and from the 2000s, what's wrong with that now? Click. Okay, so basically, I will not play something wrong here. So basically, from 2003, that LJ had the conference, even still on the website, I digged out there, okay? And then 2004, I was involved as a PC chair with Professor Him and Jen, two of us, becomes a PC chair, and he's on the business side, I'm on the CS side, and then we have a bunch of people coming in, and then 2005, Service Congress started because LJ had two conferences, the SCC and the ICWS. Then Patrick, Jiazhang, they are starting helping with this conference until today, right? So, and LJ started this service computing, a journal, after a few other journals with Spinger, and he founded this service computing journal. I am the pleasure to be the second EIC, and we're going to have the third EIC from the 2017 on, so people interested can apply. And then cloud computing was started joining the Congress in 2009, I think, somewhere around that. So these things are moving, and our size of the conference grows. Okay, so it's really remarkable. It's something that I remember people tell me about the World Wide Web. When I was a PhD student, I said the World Wide Web is something good because I do World Wide Web research. They said, don't submit there. That's crap. Okay, that's a conference crap. Okay, so don't send to that. Okay, send to decent conference like VODB, Sigma. You say, don't send to that conference. Now you see today, that conference is top conference. Okay, everybody loves to go there. There are thousands of people every year. Doesn't matter where you go, what conference, what's location the conference choose. So it's beautiful growth, right? So hopefully our conference will grow, eventually be bigger and bigger, and the community gets bigger. Okay, I'm done. Thank you. Questions? You guys gave me a few questions, right? Yes.
Well, thank you so much for such a great and thought-provoking presentation. Could you share your thoughts about real-time big data analytics? Does the real-time factor change? Is that a game changer in terms of the technologies and the approaches that we use to get insights?
Yeah, beautiful question. Very, very good question. It's a very hard question too. So real-time analytics demands actually real new algorithms. But I still think the real-time analytics has to benefit with the offline analytics first. It's like a data warehousing. If you know data warehousing, we first massage all the data into cubes, and we store those cubes inside the disk. And then we do real-time on-demand CEO a question answering. So we are predicting what the CEO is going to answer. And then we try to massage the cube quickly and then give that. So I think a real-time analytics should follow that kind of similar analogy. So take offline analytics, create a lot more pre-computing models, and then predicting what your decision maker is going to ask. And then try to quickly assemble that using some new techniques. I think that's one way to go. Maybe there's other ways, but I think the data warehousing is one of the great examples how the real analytics and offline analytics can be combined.
Thank you very much. Actually, my name is Kelvin from Hong Kong, and my background is from Macau, so it's very interesting and very meaningful for me because at the same time, we are doing some big data analysis with the clinicians, and we find that there are some communication gap between us. For example, as you mentioned, or maybe you recall, data analytics as a service, but I'm just wondering whether this meaning of the service is supporting service or something like because the role of clinicians may think that the engineer or something like this is supporting.
Okay.
But I know that in this conference, all of you are quite professional and you have some idea of research that improves the world.
Okay.
This is true. But how can we make the role
Right.
better communication together? Thank you very much.
Right. So the question really is how to interpret the service. What is the service style of thinking? So this is also something I have been thinking. Basically, when you make a program to solve a particular application problem, you just write code to solve that. Then you're done. It's beautiful. It works. Okay. But if you use a service-oriented thinking, it's like a software modularization. So not only that, you have a beyond that tool. So you are thinking, okay, I'm going to write a program to solve this problem. But this problem, I'm going to solve it in a service-oriented fashion. Meaning, that I need, number one, I need to package it so that you have a clear interface. People can use it anywhere they want. Can be directly in front of the screen, can be remotely from network. That's number one. Number two, I want a service-oriented because I want to also capture certain service-based features so that in the future I can tune it, I can actually interact with other services. So that's basically give you a service style of thinking. And so by thinking the programming practice as a service style, that gives you a lot more a criteria, functional, no functional, that actually helps you to make your code can be used for other purposes. So basically, you put one effort, you get three a benefit.
So one more small question. How do you see the interdisciplinary research?
Okay, that is a very good question too. You see, service doesn't come from computing, from economics, from business. You know, business people love service. If they have a product, they don't say we sell you product because they want to sell you product and services. Why? Service makes a lot more money. And humans love service too because I had a product, I don't know how to install this, I don't know how to install that. Can you just do it all for me? I'll pay, right? So service becomes a way to packaging the delivery of product, packaging the capability of the product. So that's the same thing. Computing is learning how to package computing as a service. Packaging the different computing modules, capabilities as a service. So we can deliver to any user in any way they wish to use this particular service. They don't have to understand it. So a lot of people talk about transparent computing, invisible computing. All they want to say in the future is the services. They don't want to see computing. They don't want the word of computing. So they just want the services. So then therefore, all the computing services and the business services, they're the same. They're just business services. That's where we're going to head into in the future. I don't know how long, maybe not in my life, but it's probably the way we go.
Alan Porter, Georgia Tech, not the computer science. I want to share a challenge. A colleague of mine, we were involved a little bit with the IARPA, Intelligence Advanced Physics Project Administration, huge project, trying to mine full text data to get some indicators of scientific emergence. Not sure how productive we were in coding, but we were amazed at the brilliance of the data scientists in the lab. And totally dismayed at their disconnect from real application. I think the project comes down to what can we do in terms of training to connect?
Right, that's actually a very good question, very hard question, actually, very hard question. So researchers, they do research based on their limited understanding of the world, of the application. And the students do research by reading those papers who gave them description of what is real world should be. So therefore, they don't have a good understanding of that. Even me, when I was 30, probably I don't have a good understanding. By now, I'm aged enough, I see more. You see that, right? So that's why I think if the application people can give a description of the problem, and even that, I would love to publish that. Why? They don't need the technical thing. They just need to say what are the problems bothering them. For example, your experience with a large text data that didn't succeed. But we can talk about the problems. We can talk about why this is so hard, why the existing algorithm, whatever I tried, it doesn't work. Because that would help us, help the younger a student who actually do day-to-day research to really do something that are really useful rather than do something just to publish, right? Or do something just this particular thing works. I can show it a demo. Demo is beautiful, but that demo does not solve anything, right? So I think there is a gap, but it's very hard to teach it because even I tell my students, if I tell 10 things, they only remember one, and they pick the one they want to remember it. So that's why you repeat. Eventually, you think they understand. Then suddenly you find, oh, you didn't even hear me to say this. See? So that's why I think that something on the paper would really help them to read it over time. And every day they read, every year they read, their understanding grows, right? So that helps. So that's why that we LJ is inviting the vision papers, and the journal we are interested in short papers on those, because they don't have to be scientifically very in depth, but they really help students to understand it. Because we have so many, see, for example, Spark. See, the reason I do Spark research is because, see, MapReduce has a lot of problems. If you dig out MapReduce literature, they claim, they show that. They say we tried MapReduce using multi-thread instead of sprung so many Java virtual machine. Every map is Java virtual machine. Every reducer is a Java virtual machine. It's sprung a lot. But we can never beat multi-thread. I do not know what's wrong with the programming of multi-thread. We just never beat it. So multi-thread MapReduce is just lousy. That's why we launched this one. Okay? So these are basically telling you the problems. Now Spark has a lot of problems too, right? So therefore we live with two wonderful systems, but we shouldn't think they solve every problem. They don't. They only solve some problem to have us seeing the light that there is possibility to solve. There's far away from solving problems.
My question is, there is data analytics, data analysis, but what I see is that in the future, the data is also owned by different people. So there is data as a service, where there are data providers, which might have different capabilities, different qualities, and they willing to share certain part of data, not certain part of data. What are the challenges when these two models, data analytics as a service and data as a service, seem to lack it? What are the challenges? What are the parts of it? What are the additional challenges that we need to overcome?
Yeah, it's a good question too. My personal opinion is about human. Our data has different stakeholders. We don't own all our data. Credit card company owns my credit card information. Rental car company own my rental information. I have it, but they own it too. It's their data. And medical doctor owns my medical data. So the stakeholder of the data is managing the analysis on that part of the data. Therefore, if we want to protect the quality, and for each specific stakeholder, they handle the quality by themselves to their interest. Now, if the quality is wrong, then they may infer something wrong about me, and that intrudes my privacy. And then so the privacy should be protected by government or by standard. So therefore, I actually talk to IEEE Big Data Initiative people. They should do standard, right? IEEE is big; they can do standard, because there has to be a way to regulate how the data analytics going to what is the standard they should conform to obey in terms of privacy regulations. And if they infer certain things about me, they want to publish that, and then maybe they should also let me approve that. Why? Because this is the stakeholder, right? But then thinking about that, maybe there's another law degree on that, because then lawyers has to be the one telling me this is approved or not, because I do not know what is the indication of that, right? So therefore, there's a lot of things evolving. You see, in law degree today, the privacy lawyers makes a lot of money. They don't go to court. It's just a new area. So maybe there's a lot more things evolving around that. But I think data as a service is probably not there, because the data cannot be a service. So it has to be analysis of the data as a service. Data is the data you own. And as soon as you give out data, that giving out action is analysis. Maybe it's simplistic analysis, just transfer, but that is a service. That's what I think. But nobody want to give out data. The stakeholder want to hold data. That's the asset for them, right? The raw data they keep. The funny thing is, even the company has data like Google, they may not use all the data because they don't have enough programmer to program enough to understand all the data they have, right? So there's a lot of issues with doctor also have that. But so that's why we should think about what are the issues we can do. And for example, if somebody has a luxury of large data, they need analysis tools, and they cannot find it. Why? Because there's not good tools. Whatever tool you find, you use it doesn't work. So that the gap is always there. But this gap has been in the traditional computing tool. It's not just data bring that problem, right? Traditional computing has the same problem. The software doesn't work for the real applications, so therefore we have a lot of application software. We have a lot of programmers. That's why all the programmer has job has big salary, because of that, right? So that doesn't change. I don't think it will change also. But to use the service as a way to think really changes a lot. Because web can only have a search engine to dig out the surface of the content. Only because web services that makes every deep data source can be delivering the data to the client. Because every deep source would use web service to make their data available through service style. And then the cloud computing through service style, they can allow people to run machines, run softwares. So things are moving like that, right? So that's why I think a service way of thinking has some attraction. That's how I figured out so far, right? But we're still learning. I think talking to business people would be good, right? Because business people using services a lot. I mean, service is an envelope for them to make money. So that's why I think it's something is really worth to think, and the computing people should learn that. Okay, thank you.
Thank you.
Thank you for the questions.
It's the best keynote I've ever had in my life. Thank you very much. Very fun. It's really I need to meet with Eric.
Okay, yeah. Yeah, you go. I do my...
Where are the slides?
Slides is already in the...
Desktop, right?
No, in the desktop with the PDFs, right?
Okay, right.
So I'm just close it for me.
Hey, Lynn. Good to nice seeing you again. All right.
Yo, good to see you. Haven't seen you in a long time. Yeah, we will catch up.
Okay.
Yeah, Lee, we'll catch up. I think I saved it somewhere here, right? The PDF. Here. No, not this one. This one.
This one. Oh,
See
yeah,
that?
yeah.
So then we're set for...
Ejected. Yeah, second.
Save, right?
Yeah.
Then...
Let me just...
Will you be sharing the presentation?
Yeah, it's in the conference. They share it somewhere. I don't know where the web page is.
Okay, but on the web page is